Hi everybody, welcome to another video in linear algebra, section 4.6, chain of bases. Let's look at the first example. We have the set of two bases, of course, of the same vector space. Of course, when we have the same vector space, doesn't matter what the bases are, they must have the same number of vectors in the bases. So in this case, we have two. Let B1 be 4C1 and 4C2, and B2 is negative 6C1 and C2. If x is equal to 3, B1 and B2, meaning that in the B coordinate it's going to be 3 and 1. How do we write x in the C coordinates? Again, we use the script letter for the bases, but of course, you just write regular B or C. That's perfectly fine. Right. Now, since this problem will give us that, we just use directly, we say x equal to 3 times B1 plus B2 and we are given this condition. Not every problem we have this condition, but this one we do. So we're going to say it 4C1 plus C2, that is B1, and then B2 is going to be this. And then we just multiply now and combine like terms. So we have 12 minus 6 is going to be 6C1 plus 4C2. Now since x is given by 6C1 plus 4C2, we can say x in C coordinates is equal to 6 and 4. Right. Simple enough, because this problem we are given this condition. Of course, here we have a sample here. We have 3B1 and B2. Combination of that gives us that point x. Now same point x here, we have 6C1 and 4C2. Also, when we add 4C2 and 6C1, we have x. So we have the same point, but different representation because of different bases. Of course, for each basis, the representation is unique, but since the bases are different, we have different point, different representation in different coordinates. Right. Now chain of bases theorem. Now the notation kind of a bit confusing. We have the basis B and the basis C of the vector space V. Then there is the unique matrix that transform basis B to C. So this is the matrix that transform from B to C. We write like this. From B multiplied by that, so say B from B to C. So that's why we write in this kind of strange. Of course, if we could write from B to C, but since we have B on here, it go to this side to C and C on the other side, right? And this matrix, this column of this are the C coordinate vectors of vectors in the basis B, and that is we're going to write like that. The matrix is called the chain of coordinate matrix from B to C. Remember, from B to C, but we run backward from B to the right and then C on the left. So from B to C, once again, we're going to write P from B to C. Right. Of course, when we have that, we can just say we will have x x in C coordinates is equal to the chain of coordinate matrix from B to C times the B coordinate of x. Now, how do we find that matrix? Well, this is how we find that. So let B, if B is the basis and E is the standard basis, then we just going to write the set of those bases. Right? If it is the standard basis, if it is not standard basis, we're going to put C and then B. Remember, we go from B to C, so B on the right, C on the left, and we go from B to C, from right to left. And when we do the reduced row echelon form, the left hand side turn to identity, the right hand side will turn to the matrix, the chain coordinate from B to C. Right. Now, let's B1, B2, C1, C2. Those are the vectors. Will give us two bases, B and C, basis for R2. Right. Now find the chain of coordinate matrix from B to C. So that is P from B to C. Right. To find that, of course, we're going to put C on the left, C1, C2, and then B1, B2 on the right. When we do reduced row echelon form, the left hand side will be the identity matrix, the right hand side will be C, P, chain coordinates from B to C. Right. So in this case, we will write the matrix with C, -7 and 9, -5 and 7, and then B1, -3, B1, B2, -2 and 4. And we do reduce row echelon form. Alright, 2 rows for column. -7, -5, 1, -2, 9, 7, -3, and 4. And we do that, we have 1, 0, 0, and 1, 2, -3 half, -3, and 5 half. And that is the matrix, chain of coordinate matrix from B to C. Alright, next we want to find a chain of coordinate matrix from C to B. So that is P from C to B, meaning we're going to put B on the left hand side, and C on the right hand side. Then just do reduced row echelon form. Should get identity on the left hand side, and on the right hand side is the chain coordinate matrix from B to C. C to B. Right. B and C right, we have 1 0 0 and 1 5 6 3 and 4. Right, of course that identity, so we're going to have the chain of coordinate matrix from C to B equal to 5 3 6 and 4. Anything special about those two matrices? If it is the case for the matrix that go from the coordinate B to B coordinate to C coordinate, or from C coordinate to B coordinate, they should be inverse of each other, right? So let's see if it works. 5 3 6 and 4. Let's find inverse. As you see, those two are inverse of each other, and that should be the case, right? Simple enough, right? Next, let B1 be 4 4, B2 8 4, C1 2 2, and C2 negative 2 and 2, and consider basis of R2, basis of B, basis of C. First, I'll find the chain of coordinate matrix from B to C, which is that. Of course, we're going to put C on the left and B on the right and reduce row echelon form. And so to find this, of course, C will be on the left and B on the right. If it is done correctly, we should have the identity on the left, and on the right hand side the chain of coordinate matrix, right? So here we write C 2 and 2, negative 2 and 2, and matrix B, meaning the vector B1 and B2. 2 2, negative 2 and 2, 4 and 4, 8 and 4. And reduce for echelon form. Two, negative 2, 4 and 8, 2 and 2 and 4, right? So we match those two together, so we say P from B to C is equal to 2 3 0 negative 1. Next, if x is in B coordinates 3 negative 2, what is x in C coordinate? So now we write x in C coordinate equal to the matrix something times x in B coordinate. notice that we go from B to C. That's what we need in C. So we go from B to C. And so we just have this matrix times the vector x in B coordinates. It's a simple calculation. I should do it by hand instead, but it's simple enough. 0 and 2. Right, so that's what we have. So the point x in C coordinate is going to be 0 and 2. Right, so when we find the matrix, and we just do that directly. Now, indirectly. Now, can we find x in C directly? Well, that's simple enough. First, we have x of B is 3 and negative 2. So I say x in B is 3 and negative 2. That means it's going to be 3 times B1 minus 2 times B2. And we are given B1 is 4 and 4. And B2 8 and 4. Right, just combine them. 12 minus 16. 12 minus 8. So x of B is equal to that. Because in this case, that vector actually is going to be, if we didn't write anything, so this should be in the regular basis. Just say it. Let's say that. So if we are confusing, we might write epsilon there to the set of standard bases, but okay, we know that is just negative 4 and 4, the point in the standard basis. Now we want to find the coordinate in C, which we don't know what it is. So in this case, let's write x1 and x2. Right, so right, like this may be confusing. Let's just fine tune the notation. If x in B coordinates 3 and 2, so x is given by that. That makes a lot more sense. Now x in C coordinate, so x can be written as x1 times C1 plus x2 times C2. Right, just like what we have here. It's B coordinate, so that's why this is a regular x. So we don't need to write in the standard basis. So it should be the case. We know x is negative 4 and 4, negative 4 and 4, and we do know C1 2 and 2, and C2 negative 2 and 2. Right, so this is simple enough. We have the system of equation here. So we have put in the matrix form 2, 2, negative 2 and 2, x1, x2, equal negative 4 and 4. And reduce to echelon form. I mean 3. Right, so we have x1 equal to 0 and x2 equal to 2. So we have x in C coordinate is going to be 0 and 2. Of course, that's exactly what we have earlier. So just don't get too hung up with the notation. When we said b coordinate of x equal to something, we're just going to write like that. But if we're going to write x, that default is going to be in the standard basis, in this set of basis, and we can write the linear combination and so on. Right, now we do the same thing, but this time for vectors in R3. Right, now find the change of basis of coordinate from B to C. So change of coordinate from B to C. So B on the right, C on the left. We go backward in this from right to left. So what we do is just going to put from B to C. So this all order. Yeah. I'm not going to write the matrix again because we know which one is C, which one C1, C2, C3, and so on. Alright, so reduce to echelon form, we have 3 by 6 here. Right, C1. C2, C3, B1, four, negative 1 and 3, 5, 5 and 2. Right, when we do that, we have the identity matrix on the left. On the right hand side we have 2, 2 and 1. Of course, this is going to be the chain of coordinate matrix from B to C. So that's going to be that matrix. Just make sure that I enter it correctly. Right. Now, let x in B coordinates given by that calculate x in C coordinate. So once again, if we want to see x in C coordinate going from B, because that's given, we're going to multiply by matrix from B to C. B on this side, C on the other side. So we just set the matrix here. times this. Right. So we have this matrix times this column. We have -5, 23, and 0. Right. So in C coordinates, x is equal to that. Now, can we calculate xc directly? We know x in B coordinates is equal to that. That means x can be written as a linear combination using this number, 4 times b1 minus 9 times b2 plus 5 times b3 and that will be 4 times b1 9 times b2 and 5 times b3. Right. Just going to type the first one, 4 times 6 minus 9 times 4 plus 5 times 5. That's 13. And then 12 plus 9 plus 25. That's 46. And then 12 minus 27 plus 10. Right. So x in the standard basis is given by that. Now we can write this in the basis of C. So in C coordinates, we can write x as x1 times c1, x2 times c2, and x3 times c3 equal to x. So we write the equation. We will have c1. We put c1. I put this in the matrix. X is going to be equal to 13, 46, and -5. And now this is just the matrix system. I mean the vector form of the equation. C1 we know is from the original problem 2, 0, and 1. C2 1, 2, 0, and C3 1, 1, 1. Of course, we put in the dimension augmented matrix, that on the right hand side, that on the left. Or we just say it. We're going to put this C1, C2, C3, X, reduce row echelon form. Yeah, that to solve this system. C1, 2, 0, and 1. C2, 1, 2, and 0. C3, 1, 1, and 1. And then we just have 13, 46, and -5. Right. So do that. We have the identity on the left hand side, and on the right hand side -5, 23, and 0. Of course, in this case we have x1 equal to -5, x2 equal to 23, and x3 equal to 0. Or we write the coordinate of x. Write x in the c coordinate is equal to -5, 23, or 0. So whether we calculate it directly like this. Or we use the formula, we should get the same thing. Of course, when this get more and more complicated, using the matrix form like that is a lot more convenient. Right. But that's what we call the chain of bases. We get a number from one basis to another basis. So from one coordinate system to another coordinate system, and to link that, we're going to use that matrix called the chain of coordinate matrix from B to C. Right. So that's all I want to cover in this section. Thank you for watching. As always, see you in another video in algebra.